So we got 120 Newton meters times the diameter of D. I'm allowed to make mistakes. It's Monday. All over. The diameter at C is the exact same diameter as it was at A. It's 50 millimeters. We get 600 Newton meters equals the torque at D, which we know is the torque at E, right? So torque at E is 600 Newton meters, right? So now you know in a general sense what's going on in your transmission in your car, right? As you change gear ratios, it allows you to increase the torque applied at the motor to the torque that's applied at the wheels, right? We also, at this point, we're not going to, we also could continue to calculate a number of things related to this system, right? We could figure out what the stresses are based on the applied torques to each of our shafts to make sure that they are adequate, right? We could also figure out the angular rotation if there was an alignment issue with this, right? So we could calculate tau of the shafts, shear stress of the shafts, or rotation of the shafts. And so on. Any questions there? Remember, you have a homework due on Thursday, right? By 5 p.m. Quiz is available on Wednesday till Friday or through Friday, right? All right, we're going to start power transmission, okay? The big things here, well, I'll say, work, power, and energy, okay? Work, right, denoted by this big W. Anyone know what the definition of work is? Force times distance. Force times distance. So if work is force times distance, and we're looking at torsional systems, right? The force that we have, that we've been working with, is torque. And the distance, right, is our rotation. Or T times phi, right? We've dealt with these already. So if we wanted to figure out how much work are we applying to a system, right, or have we done, we would just take our torque and multiply it by our rotation, okay, or phi. Power, on the other hand, is the rate of work. Essentially, how fast you can work. Right. The way I was told the difference between work and power is, right, if you had a semi, right, a big tractor trailer you see going down the interstate, you started in New York and you went to Los Angeles, right? And both of those semis had different amounts, like different size engines in them, right? One had the size of a lawnmower, okay? And the other one had a typical like 6.25 horse, like Cummins or Detroit in it, okay? And they started in New York and they were headed to Los Angeles, right? Both of them would do the same amount of work to get from New York to Los Angeles, right? Force times distance. It would take a certain amount of force to move all of that, the goods in the trailer, right, from New York to Los Angeles. one of them is going to get there faster than the other, right? So it can do the work a lot faster. So that would be the larger engine, right? Would have more power in it, which would allow that tractor trailer to move from New York to Los Angeles faster. But they would do the same amount of work, okay? So that's how I was always taught the big difference between work and power is. Energy, on the other hand, is the total amount of work done, right? So it would take the same amount of energy for both of those semis to get from New York to Los Angeles. One would be doing it faster because they can apply more power, but overall they're going to be doing the same amount of work and exerting the same total work done, right? So total amount of work done, right? So if power is how fast you can do work, right? It's essentially how, in terms of time, right? It's how fast you can do something, or speed related. So we would say that power, P, right? Change in rotation over time, or torque times d phi dt, right? Rotation angle over time, how fast something's rotating. Right, so power, P, is the change in work over time, right? dw dt, maybe we'll make this big D, big W, right? That would be right, if you had a constant applied torque, it'd be how does your rotation angle change? Well, how does your rotation angle change? Well, that's just the speed of rotation of the shaft, right? So T times omega. This is rotational speed. We know that phi, as we've been calculating, is calculated in radians. Well, omega is radians per second. Right? Rotational speed, radians per second. So if we wanted power in the SI, system of units, the international, we've got the watt, right? Everyone's familiar with the watt. We've got watt light bulbs, right? We've got kW generators. So we have a watt, or W. What is that? Well, that is a 1 Newton meter per second. Or Newton meter radians per second, right? Radians unitless, so 1 Newton meter per second is the same as a Newton meter radians per second. In our US units that no one else on the planet really uses except for us, right? We have torque times omega, which is our rotational speed. Torque is in pound-feet. Rotational speed is radians per second. So we get pound-feet per second, right? No one uses pound-feet per second, okay? When we talk about power, what's another unit of power? We have watt, horsepower, right? So what do we use? Well, we use horsepower. Yeah, it is actually. But it's also 550 pound-feet per second is one HP, okay? One horsepower. And as you mentioned, 1 horsepower is approximately equal to 750 watts, just from a comparison standpoint, right? So last semester, so I mentioned, well, technically you could walk into, right, if you said, wow, there's a lot of lights in this room, right? There's a lot of watts in this room. You could say there's a lot of horsepower in this room, okay? Which is weird, right? So like, I think I got down a rabbit hole here, so I'm gonna share it with you. One T8 lamp, right? Which is pretty much a fluorescent lamp. They're either T5s, T8s, or T12s, okay? So T8, just the little 4-foot sticks, is about 44 watts, right? So if we had 17 of those in this room, we have at least 17 of those in this room, right? That'd be 1 horsepower, okay? All right, random, I know, but it's intriguing to me, okay? Your vehicle, right? If you had a nice pickup, okay, probably puts out close to 300 horsepower, right? That would be 5,000 of those 4-foot T8 lamps. 5,000. That's crazy, right? It's a lot of power, right? A lot of horsepower, okay? So there's not a lot of horsepower in this room, right? If you think about it. So anyway, 5,000 bulbs for about 300 horsepower, okay? Well, rotational speed, right? In the SI system of units, we can use radians per second, but a lot of times rotational speed is denoted in 2 different units. Anyone guess one of them? When you're driving your car, right, you usually have a speedometer, and then you have another gauge. What's the gauge? RPM, right? So rotations per minute, right? So we've got rotations per minute, and then the other one, right, hertz. Anybody heard of hertz, right? Electrical outlets is putting out 120 volts at 60 hertz, right? It's a sine wave. That's how the voltage is moving through our buildings, right? So hertz. So we have rotational speed measured in either hertz or RPM, right? Hertz is a rotation per second, right? So the power in our outlets, 120 volts at 60 hertz, right? So that's the cycle. It does a 1 sine wave rotation every 60, or 60 of them per second, okay? Or 1/60th of a second. So rotation per second, we call this frequency. Right? Well, omega, right, our rotational speed, omega, would be that frequency times revolutions per second times, well, now we know we have 2 pi radians per revolution, right? So frequency is revolutions per second, right? We need to get it to radians per second. So we do 2 pi radians is 1 revolution, right? So 2 pi times the frequency is radians per second. Oops. Where this is our frequency. What does that do to our power equation? Well, it just adds an extra term there. So now we can say power, right? In terms of hertz, right? If we were given hertz, is speed times, or is torque times rotational speed, which would be the same as torque times 2 pi times the frequency, right? So that would give us our power. Well, we know we also have RPMs. Which is revolutions per minute, usually, RPM, right? So omega, right, rotational speed would be what we'd call N RPMs, or revolutions per minute. That got a little crazy. revolutions per minute. Well, we need to get this to radians per second, right? Well, we need to change the minutes to seconds. So 1 minute, 60 seconds. We also need to change the revolutions to radians. Well, we know we just did this, 2 pi radians per revolution. We get 2 pi n revolutions per minute over 60. And this is all radians per second, right? So n is RPM. So what does that do to our power equation? Well, power we know is torque times omega, or torque times 2 pi n over 60. All right, or pi n over 30. So those are our 2 big power equations, okay? So let's work through implementing these, okay? In this case, we have a solid 40 millimeter diameter shaft. It's rotating at 560 RPM with a maximum shear stress of that shaft that's allowable, right? Well, at this spinning rotation, right, and the amount of torque provided, has a maximum shear stress, right, of 85 megapascals. So they want us to determine what's the power being delivered by the shaft, okay? Well, our 2 big equations here, right, we have our power equation we just derived right there, right? Power is torque times 2 pi n over 60, n being revolutions per minute. That's what they gave us. So I'm going to say we're going to need this equation, 2 pi n over 60, right? Well, we've got another equation that we've used that relates torque, right, applied torque, to this shear stress in the shaft. Well, that's our T equals tau max, right, times the polar moment of inertia all over our maximum radius, right? We've used that equation a number of times already. Well, we ultimately want to know the power being delivered, right? Well, that means we need to know all the stuff on the power equation. When we know everything there except for T, well, T we need to get from our other equation. If we look at that other equation, right, they gave us the diameter of the shaft. We've already talked about, right, I've given you equations for the polar moment of inertia. Got that. Obviously, if we know the diameter, we know the maximum radius. And then they told us that when it's operating, right, under its applied torque, it has a maximum shear stress of 85 megapascals. So we have everything in that equation. So we're going to take that equation, calculate T, take T, plug it in, and calculate power, right? So we're going to take T and plug in there, right? Well, out of that torque equation, right, we need tau, J, and C. Polar moment of inertia, we know if we know the diameter is pi over 32 of a solid shaft, the diameter to the 4th, or pi over 32 times 40 millimeters to the 4th. What does that get us? Well, 251,327 millimeters to the 4th. Maximum radius in that equation is just d over 2, right? So 40 over 2, 20 millimeters, right? Now we can use our equation knowing that the torque applied is our maximum shear stress, which would be 85. They gave us in megapascals. I'm going to convert to newtons and millimeters so we can track units here, right? Newton per millimeter squared is a megapascal. We're going to plug in J, 251,327 millimeters to the 4th. Divide all of this by our maximum radius, 20 millimeters. I'm going to divide this by 1,000 newtons per kilonewton So what does that do? Well, that gets rid of, right, 3 of these. Gonna get rid of the newtons. We're gonna end up with just kilonewtons. So I'm gonna say torque is 1,068 kilonewton. Oops, that's not the conversion I wanted, sorry. I jumped. I'm gonna say there's 1,000 millimeters per meter, right? So now I'm gonna get rid of all my meters, or millimeters. I wanted it in Newton meters. If I can erase. So this is Newton millimeters, right? 1,068 Newton millimeters. Or sorry, Newton meters. Wow, just doing a terrible job today, guys. Newton meters. Sorry. Okay, got it. So now that we have our torque, we can plug that torque into our power equation, knowing that we know the revolutions per minute. They told us that was 560, right? 560. So power equals torque 2 pi n over 60, or 1,068 Newton meters times 2 pi. Gotta get the 2 in there. 560 revolutions per minute, all over 60 seconds. So what does that get us? Well, that tells us the power in watts is 62,639 Newton meters per second, and we know that is the unit of watts, right? So here, if we divide by 1,000, we'll get our typical units of 62.6 kilowatts. Right? That's straightforward, right? We have our governing equations that we've developed, right? We related torque to stress in our shaft. Once we know torque and we know some sort of speed associated with that torque, right? Revolutions per minute, or hertz, right? Revolutions per second. We can then develop the power that is being supplied by that shaft, okay? Similarly, we can work backwards, right? And now we're gonna say, okay, well, what's the slowest permissible rotational speed for a given motor, right? So in this case, we have a motor at A. It's supplying 25 horsepower, okay? 60% of that power is taken away at gear C, and the remaining 40% is taken away at gear D. Right? They tell us that the segments 1 and 2 are pipes, or steel pipes. Outside diameter is 1.5 inches. The wall thickness, I'm going to change this because I went through and solved this with 0.125 inches, and I'm lazy and I don't want to redo it, so we're going to change that to 0.125 inches, okay? The diameters of pulleys A and B, right? So A is 4 inches, B is 14 inches, so you can imagine, right? We're going to be able to increase the amount of torque provided, or we're going to decrease the speed, right? Because our gear ratio flips as we go from moving torque to moving rotational speed or distance, right? It was either RB over RA, well, it's RA over RB. They say the allowable shear stress in the steel tubes is 8,000 PSI, and they tell us, well, what's the slowest permissible rotational speed, okay, of the motor in order to maintain that shear stress. So if we've got tau allowable equal to 8,000 PSI, they want us to find omega allowable. Right, we're going to find it in RPM. of this system. Okay. So what's our equation for power? Yeah.
Quick question before, on that last one, that last answer, is that kilonewtons per second, or is that,
It's Newton meters per second.
oh, it's kilowatts, gotcha.
Yes, kilowatts. Oh, yeah. That's all right. I'm the one with the shitty handwriting. Okay. What's the equation for power, though? Jess went over it. Yeah, torque times rotational speed, or T times omega, right? So that's one equation we know we're going to be dealing with, right? Because we have some applied power at A. And applied power is going to give us some torque, right? And a rotational speed, right? That torque, as we know, is related to our maximum shear stress, right? Based on the dimensions of our shafts, right? So you can, as you can imagine, right? If torque is based on the shear stress, if we limit the shear stress, we're limiting the torque, right? And if power is set P, right? If we're limiting T, then we're gonna have to limit omega, right? Because there's only gonna be so much power coming in, right? So this is gonna be 25. Torque, right? We can only handle so much torque because we can only handle so much shear stress. And so in order to make up the difference, right, if torque is limited, we're gonna have to adjust our omega in order to reach our 25 horsepower, okay? So that's what we're gonna do. Well, if we start by looking at the amount of power, right, in each of the shafts, right? This is an equation that relates the power, right, and torque and shear stress at any shaft in the system, right? So if we're looking at this shaft, we know that shafts 1 and 2 are the same dimensions, right? They don't change cross section. And so we really want to look at the largest, the shaft with the largest amount of power, right? Because the largest amount of power is going to give us the slowest rotational speed, right? It's like most power will result in the limiting speed. So if we start by looking at a power diagram. So this is gears A and B, right? A is going to transmit power into B, right? The gear at B. And then that power is going to be in this shaft. Well, they told us that 60% of that power is going to be taken out at gear C, right? So C is about halfway down, and we have D at the end. Well, we know that we're putting in some amount of power. They told us it was 25 horsepower, and then 60% of it gets taken away at C. Right? So we've got 10 horsepower that's in the second shaft. Well, because our power is the most in shaft 1, right? The greatest amount of power is going to be limiting, what's going to be limiting our slowest permissible rotational speed, right? Because as we increase, right, or as we decrease the rotational speed, right, we decrease the amount of power. So if we're spinning this shaft right here, right, and we're in shaft 2, we can spin the shaft slower to get 10 horsepower than we need to spin it to get 25 horsepower. So we're going to look at the 25 horsepower shaft section to get the slowest speed that we can rotate in order to deliver that power. Okay, so section that transmits most power will be the one that results in the limiting speed. One thing to note here though, right? That only is true because we're holding everything else constant, right? If we're going for the maximum power, so the slowest speed, right? The torque's gonna be the same because it's based on 8,000 PSI. If shaft 1 and shaft 2 were different cross sections, right? Had different diameters and pipe thicknesses, right? And had different materials and different towels, the torque between them, right? The allowable torque between them could change. If the allowable torque could change, then it would change our relationship. So that would say, I would say based on constant shafts, right? It's the same shaft from B to D. So we want to find our maximum torque, right? That would be our next step. Because our maximum torque is then going to be, right? Our two knowns are our power and our torque, and we know the torque based on our maximum shear stress. Once we find our maximum torque, we can then find slowest speed. Okay, so let's start by saying our minimum speed, right? If we rearrange our power equation, we know power, we're gonna know torque. Our minimum rotational speed is the power delivered divided by our maximum applied torque, right? Where we know our maximum applied torque is the maximum shear stress times the polar moment of inertia over C. Well, if we just calculate our known values in that equation on the right, we've got our radius or diameter of 1.5 inches. I'm going to divide that by 2 to get our radius, 0.75 inches. J, because it's a pipe, right? It's pi over 32. If we're still looking at diameters, outside diameter to the fourth minus the inside diameter to the fourth. We do all of that, we get 0.34 inches to the fourth, okay? Now we can calculate our maximum torque, right? So that's essentially saying we're limiting our shear stress to 8,000 PSI, right? That's our tau max, they told us, based on this steel, okay? Our polar moment of inertia is based on the size of the pipes we decided to use for the shaft, and same with our maximum radius. So we can just plug everything in. We're gonna get, say, 8,000 pounds per square inch. We're going to get 0.34 inches to the fourth, and we're going to divide all of this by 0.75 inches. We get 3624 pound inches if we follow units. If we divide this by 12 inches per foot, we get 302 pound feet. Right? So that is the maximum amount of torque you could apply to either one of these shafts, and you would reach your maximum shear stress. We know omega is power over the maximum torque. We have 25 horsepower. I'm going to multiply this by 550 pound-feet per second per horsepower. And then we're going to divide all this by the maximum torque, or 302 pound-feet. We get 45.5 radians per second. Well, we wanted an RPM, right? So we got omega equals to 45.5 radians per second. And we know that in one revolution, there are 2 pi radians. And we know that in 60 seconds, we have 1 minute. We get 435 RPM. But we're not done yet, right? Got one last step. We're going to get through it here. Okay. This is the minimum rotational speed of our shafts, right? The motor and the shaft are connected through gears, right? Through our pulleys, which have varying diameters. So the speed with which the motor has to drive is different, right? In order to get the speed that's required in the shaft. And so how does that work? Well, the RPM of the motor equals omega of the shaft times our gear ratio. Oops, ratio, which is 435 times 14, which is the larger gear, the gear of the shaft of 1, over 4, which is the shaft of the motor. So the RPM of the motor equals 1,522 RPM. And I think that kind of makes sense, right? The motor has a smaller pulley on it, a smaller gear on it. So it's going to rotate more in order to rotate the larger gear of the shaft, right? 1 revolution. So we had to up that RPM. Okay. Don't forget the homework or the quiz.